Hi, this is Sarah Burke. I am a recent graduate in the PhD program at Arizona State University. Today I'm going to be talking about some of my research in my dissertation that was done on behalf of the Science of Test Consortium. The main topic for this talk is how to select the top N items in a list that have been evaluated across multiple criteria. This method uses a layered Pareto Front approach, and our application that we present here is in the Department of Defense, where they want to select the top, say, N subpopulations in a stockpile. This work was done in collaboration with several people, so Christine Anderson Cook at Los Alamos National Labs, Lou at the University of South Florida, and my co-advisors at ASU, Connie Bohr and Doug Montgomery. So the outline for this talk, well, we're going to start off with the motivation of the problem and introduce the stockpile application. This will be followed by the methods used in this algorithm. It incorporates Pareto fronts and layered Pareto fronts to come up with the final solution set. And then I present the application using an add-in that I built using JUMP. And so in this talk I'll show you the steps in the program and all of the output, and in a separate video I will show you how to actually use the add-in in JUMP. And then finally some concluding remarks. So our motivation for this problem is that we have multiple criteria that we can evaluate, and our goal is to identify the top N solutions to accomplish some goal. Right? Using multiple criteria allows us to have a richer and more realistic decision, rather than just focusing on one criterion or one objective. So the problem has several given things that we have to take into account. So what we assume is known is that we have a list of objects that have been evaluated on multiple criteria. Our goal is to select, say, N objects from this list. So then the question is, how do we choose what the best N items are while trying to balance these competing objectives? The application that we consider is in the Department of Defense. So they have a set of subpopulations in a stockpile and a certain number of resources to give to these subpopulations. The managers need to decide which of these subpopulations require the most care or most attention, and they're going to give those resources to those N subpopulations. Right? But they only have so many resources to give, so they don't want to just select one, they want to give it to several. How do we choose which set of these subpopulations to give the resources to? They have several criteria that they would like to balance. So one is a reliability metric, one is urgency, and the third one is consequence severity. So a few details about each of these. Reliability takes into account several measurements or metrics on reliability. So for example, the current reliability of each subpopulation, the proximity of the reliability to some certain threshold where the subpopulation would need to be removed from service, so it was at a point where it could no longer reliably be used, or the rate of change of the reliability as the unit ages. The urgency metric takes into account, well, how many reserves of the subpopulation do we have relative to what our current or projected usage rates will be. This also takes into account, are there similar munitions that we could use in place of a particular subpopulation. Right? If there are similar ones that we could use in its place, right, there's less urgency to give resources to a particular subpopulation. If it's a one-of-a-kind subpopulation, we can only use it, right? That's going to raise the urgency metric. And finally, consequence severity, which is a measure of the impact of a shortage of a particular subpopulation in current and projected military exercises. So most of these metrics using, or these criteria, have multiple components to them. So how do we get one overall measure for each of these? Well, each criterion is evaluated or determined by multiple subject matter experts. The experts assign each stockpile a score for each of the criteria 0 and 10. And here a larger value is going to indicate more dire needs. So the more urgent or the higher the consequence severity, the higher the score, for example. Right? So that's our application, our motivating example. Now, how do we go and select what the top N subpopulations, or the most critical subpopulations, are from our collection of subpopulations? Well, the methodology we're going to use involves Pareto fronts. So here is a quick review or introduction to Pareto fronts. A Pareto front is the set of non-inferior points in a data set. So the goal here in using a Pareto front is to eliminate dominated inferior points from further consideration. And this allows us to balance multiple criteria simultaneously. So here's an example of a potential data set that's been evaluated on 2 criteria. So each point in this plot here represents the result for a possible solution. And let's suppose that for each of these criteria, the larger the number, the better. So ideally, we'd love to be at this point here, representing the utopia point, right? But this utopia point rarely exists in real life. So you'll note that there isn't actually a solution at this point, right? It's just where we would love to be if we could. So what the Pareto front is then, is it's the set of points that are the dominant solutions in this data set. Right? So for a solution to be on the Pareto front, it needs to be equally good. Each criteria needs to be equally good compared to all of the other solutions, and strictly better on at least one criterion. Right? So here, any solution in this region, these are the dominated or inferior points, they're always going to be beaten out by one of these solutions on the Pareto front in at least one of the criteria. So looking at the Pareto front can be really helpful when you want to find, say, the best or one optimal solution. But in this scenario, we don't want just one solution, we actually want a subset of optimal solutions. In this case, only looking at the points on this Pareto front might be a little restrictive. For example, there are several solutions depending on how we prioritize each of these criteria that might be worthwhile second or third best choices to include in our final solution set. So for this reason, we extend the methodology of a Pareto front and use what we call a layered Pareto front. So to find a layered Pareto front, we first find the points on the first Pareto front. So this is the same example we saw before. We find the set of dominant points in our data set and label these as layer 1 solutions. Then we're going to set these aside and remove them from the obtainable criterion region and look for the next set of dominant solutions in the remaining set of points. So here we have the next set of dominant points from this remaining set. We're going to label these as belonging to the layer 2 in the Pareto front, set those aside, remove them from the obtainable criterion region, and look for the next set of dominant solutions. And we continue this until we have, say, M layered Pareto fronts. And here's an example with 5 layers in our Pareto front. So here is our layered Pareto front, these points highlighted. Every other solution that's been grayed out has been eliminated from further consideration, right? Every solution in this region is beaten out by at least one solution in the layered Pareto front on at least one criterion. Right, so using these layered Pareto fronts, use these layered Pareto fronts to identify the top N items in this subpopulation. So the general algorithm is divided then into 2 different phases. In phase 1, it's an objective stage where we eliminate points or solutions from further consideration. So this is strictly objective and where we find the solutions in the layered Pareto front, like we just saw. Phase 2 is a subjective stage which allows us to analyze the trade-offs between identified solutions. So this brings in the subjective nature of decision making. Right? If we have multiple managers trying to decide the most critical subpopulations, different managers might have different priorities on which criterion is more important. Right? So this phase allows us to examine the trade-offs between identified solutions and how we might change our decision depending on how we prioritize the criteria. So we'll go into details of each of these steps, but in general, this phase involves scaling the criteria first, so they're on a common measurement scale. We then calculate a desirability function score for different combinations of weights on the criteria for each of the items in our list, and then use several graphical tools to make a final decision. And what we do here is we don't provide the user with the solution. What we want to do is provide a set of options so that you can come to a decision based on your own priorities. Right, so let's take a look at the example that I mentioned before with the Stockpile application. So this is simulated data, but the application is still actually is a real example. So let's suppose that we have 100 subpopulations in our stockpile, and the managers need to identify the 4 most critical subpopulations. Now, I mentioned metrics for reliability, urgency, and consequence. For the purposes of illustration, let's suppose we just consider reliability and urgency. Right? Which 4 subpopulations should we choose to provide resources to? So this is what the data set looks like, right? The index is just a identifier column just so we can keep track of the subpopulations. And then we have our metrics for reliability and urgency and consequences also there. So recall as well that larger numbers indicate that these are more critical. So the larger the number, the more critical. Right? I developed an add-in in JMP, which I will show you as we go along, and also show a demo of how to use it in a separate video. But this is the first menu that comes up in this add-in. It's a dialog window that allows you to specify the appropriate columns for the criteria or the objectives, and then an ID column so you can keep track of the solutions. So in this data set we have index, which is our ID column. It's just numbered 1 to 100. And then we have reliability and urgency as our criteria that we'd like to evaluate. Right? The next window that comes up is a lot of options for each phase. So we're going to go through these phase by phase and break down all of the options. So the very first step is to enter the value of n. So how many solutions in your subset would you like to identify as the most optimal? Right? In this scenario, the managers want to identify the 4 most critical subpopulations, so we've entered in 4. The next set of options, we're going to look at the phase 1 setting. So this is, again, purely the objective stage, and this is where we want to eliminate the dominated points or solutions from further examination or further consideration. So this is where we're just finding the solutions that are on the layered Pareto front. So the first step here is to enter the number of layers that we would like to extract. Now this number you can change. Ideally, you could just leave it as the value of n. I'm just going to show you what it looks like with 3 layers. Having it with 3 or 4 layers would work just as well. The recommendation after a simulation study is to let this value equal to the value of n. You don't lose any information and the algorithm still works fairly quickly. The next step is to identify whether the criteria or objectives are optimized by maximizing or minimizing. In this example, larger values meant that the subpopulations were more critical, so a larger value is better to be able to identify the most critical subpopulation. So each of these boxes are checked for this example. Right, so now we're going to look at the example of the output of phase 1 in this add-in. Right, so the first thing that you get from this output in phase 1 is an interactive scatter plot. So this allows us to visualize the points or solutions in the layered Pareto front, and each layer is labeled with a unique symbol. So here the highlighted points belong to layer 1, here are our layer 2 solutions, and here are the subpopulations in layer 3. So if we consider a 3-layer Pareto front, right, we initially started with 100 subpopulations. We needed to choose 4 of those. Now we've eliminated 80 of those. Now we just have a subset of 20 subpopulations that we need to look at. So this has really helped make our decision more manageable. We don't have to look at 100 options. Now we're just down to 20. One thing to take into account is how to handle ties. So what if 2 or more points or solutions have the exact same values for each criterion? Right? In this stockpile application, for example, subpopulations 11 and 37 have the exact same values for reliability and urgency. So like I mentioned before, to be on the Pareto front, a solution has to be at least as good in terms of all of the criteria compared to the other solutions, and strictly better than at least one of the criteria. If a solution is on the Pareto front and there's another solution that is tied, it has the exact same values to a solution already on the Pareto front, we're trying to determine, should this other solution also be on the Pareto front? Well, if we're comparing it to each solution, right, it is at least as good on all the criteria, but it's not strictly better than at least one because it's tied. They have the exact same values, right? So traditionally, another solution that's tied wouldn't necessarily be put on the Pareto front. Well, this isn't an ideal outcome, particularly in this application. We don't want to miss a stockpile in our solution set simply because it had the same values for our criteria or objectives. So what we do is we choose a representative point while building the Pareto front. So say a solution is on the Pareto front. Before we output our final solution set in our layered Pareto fronts, we do a final search to see if there are any tied solutions left. And if there are, it's added to the same layer of the Pareto front as its matching solution, right? So any one that has the same values. So we don't lose any potential solutions later on. Alright, so that was phase one. It was the objective stage. We've just eliminated the dominated points from further consideration. Now we're going to move on to phase two, which again is our subjective stage. We can bring in the subjective nature of decision making, and because of this, we give many options for you to use. So we'll go into details in a little bit about each of these options, but here's just a summary. So the first step is to select a desirability function to be able to combine each criterion into one overall score. So for example, here I've selected the additive desirability function. Right, there are several graphical options that you can select. We will go into detail about each of these plots in a little bit. And then finally you can select scaling settings. Now, we talked about scaling briefly before. Why might we want to scale? Well, if you have multiple criteria or objectives evaluated for each of your items in your list, they're likely to be on different measurement scales. And we're going to take each of these criteria, weight them, and then combine them into an overall score. If they're on different measurement scales, we might have some solutions identified as dominant purely because they're on a larger measurement scale, which can be a major disadvantage. So our very first step then is to scale each criterion to values between 0 and 1. So the way we do this is we have our formula depending if the criterion is maximized or minimized, and we scale it between 0 and 1 using these worst and best values. Now, how do we define best and worst? Well, it depends on what your objectives are, and we have 4 options for you to choose from in this add-in. So the first option is fairly standard. So here we define the best and worst values as those from the solutions that are in the layered Pareto front. So from phase 1, we get our set of solutions in the layered Pareto front, and then we'll define the best and worst values for each criterion just using that subset of points. So for example, if the criterion is maximized, the best value would be the maximum value for that criterion from the points in the Pareto front, and the worst value would be the minimum, right? If you were minimizing the criterion, the reverse would be true. Right, the second option is to define the best and worst values using the original or entire data set. So rather than using the subset of solutions that we get from phase 1 of the algorithm, we use the original data set. The other options give you a little bit more control. So for example, you can select the best value as being the solution or the maximum or minimum value from the solutions in the front, and then you can enter in what the worst value is. Or you can have total control and enter best and worst values for each criterion. Now these last 2 options give you some more flexibility. So for example, if you have target values for the best and worst values for each criterion, you can use those rather than what is actually there in your data set. The other option when you might want to use this is if you have criteria that are on wildly different ranges. So for example, say one criterion ranges in values that are, say, good to excellent, whereas another criterion has values that range from very poor to excellent, that differences in ranges is quite wide comparing the criteria. So allowing you to enter in best and worst values for each objective or each criterion can help account for those types of discrepancies. Right, so the scaling choices that you might pick will and likely will change what your final solution set is. So you should carefully decide, what's your priority, what is your data set like before you make this choice in scaling. Once you have your criteria scaled, then we want to combine the criteria into one overall desirability function score. And here we have two options you can choose. So one is the additive desirability function, and the other is the multiplicative desirability function. So here the ZIJs, again, are the scaled criterion values, and the weights, WI, are defined between 0 and 1. They sum up to 1 across the criteria. So these weights represent the priority that you might give to one criterion over another. Which desirability function should you use? It depends on your objectives. So for example, a multiplicative desirability function tends to penalize low criterion values more than the additive desirability function. So if you want to avoid scenarios where if you have one poor value for one criterion for one particular solution, but another criterion has a very high value, the multiplicative desirability function is going to tend to penalize that solution more because of the very low value in the one criterion. The additive desirability function, on the other hand, is less forgiving. So if you have a particular solution that has very good performance for one criterion but not great performance for the other, the additive desirability function is going to penalize it less than the multiplicative desirability function would. So take those types of balancing decisions when you choose the desirability function. The other thing you could do is compare results. How does your solution change depending on the desirability function that you use? There are several graphs to help guide you to a decision that results from these phase 2 results after we scale and use the desirability function criteria. So here I'm going to go through the different types of plots to help you guide your decision to find the top, in this example, the top 4 most critical subpopulations. So this first plot is the mixture plot, and this allows you to compare the top 4 solutions at any given weight combination. So the x-axis contains the weight on one of our criteria. In this case, it's the weight on our reliability objective. So by default then, the weight on urgency is 1 minus this weight on reliability. This y-axis here is our ID column, right? It's the index. So this allows us to identify the subpopulation so we can keep track of them. This graph is on a black to gray scale, so a black box here indicates that it was the top solution. It had the highest desirability function score at a given weight combination. And then in decreasing intensity, you see the second, third, and fourth best options. And a white box indicates that it wasn't a top solution or a top 4 solution at that weight combination. So for example, suppose we look at a weight of 0.15. Here we see that solution 70 had the highest desirability function score, and its value was 0.94. There is some hover text in this plot, so if you hover over any box, it'll tell you what the desirability function score is for a given solution at that weight. So here we have the top solution, here is the second best solution, index 2, subpopulation 2, and then we can see the third, and actually we have 2 solutions tied for 4th place. So you can notice any ties that occur in this mixture plot. What's really nice about the mixture plot is it allows you to see how would your solution set change as your priorities change. So for example, if you have several decision makers trying to come to a decision on what the most critical subpopulations are, one person might prioritize reliability more than urgency, and another might care more about urgency. Right? So this plot allows you to say, how would my top 4 solutions change as the priorities change, or how the priorities differ? The second plot available is a proportion plot. This proportion plot is a stacked bar chart that allows you to analyze the frequency that each subpopulation is in the top 4 solutions. So this plot is on the same black to gray scale as the mixture plot, so you can identify how often any given solution is the best, the second best, third best, fourth best choice across all of the weights. So for example, subpopulation 2 was frequently a top solution no matter how we weighted. If we look back at the mixture plot, for example, we see that subpopulation 2 was a critical solution very often, except maybe in a few cases where urgency was prioritized the most. Okay, so in this proportion plot, we see, right, subpopulation 2 was a frequent top 4 solution across many of the weight combinations. What's nice about this proportion plot is it also highlights some of the solutions that on that first Pareto front layer, right? So the first Pareto front layer allows us to look at most often the best solution, right? But for example, subpopulation 39, it wasn't on the first Pareto front, it was on, I believe, the second layer. Okay, but we can see here it's still a frequent top solution. It's not the top solution ever, but it's the third or fourth best option across many of the weight combinations. But if we had only looked at the first layer in our Pareto front, right, we would have missed this potentially critical solution. Okay, the third plot available is the parallel plot. This plot allows you to examine the trade-offs of each subpopulation in the Pareto front in terms of the scaled criteria. And so here we have it on the same scale, so the worst values, right, is represented at the bottom and the best are at the top. And here we have reliability and urgency. So what do you want to look for in this plot? Well, notice that really steep lines are going to indicate that you have very large trade-offs for a particular solution. So for example, here are a couple examples of subpopulation. So this one here is subpopulation 2, which, if you recall from the mixture plot, was a dominant solution across many of the weight combinations, particularly when reliability was emphasized. So this one indicates a less steep line, okay, so it's a little bit flatter, indicating that there's less of a trade-off for the subpopulation in terms of these two criteria. On the other hand, here is subpopulation 25, which had a really high value for reliability, but didn't really compete compared to urgency. So there's a very large trade-off for this subpopulation. And here is that example, subpopulation 39, which, if you recall, it wasn't on the first Pareto front layer, but it was a top 3 or 4 choice across many of the weights. So here again we see a slightly, a relatively flat line, so indicating high performance, or I would say critical performance for both reliability and urgency, but notice that it's not the top value for either of these criteria. So it's never the most critical, but it's up there. It competes with the most critical. Alright, so now how would you make your decision? What is your top 4 most critical subpopulations? Well, using these 3 previous graphical tools together, you can start to identify, right, contenders in your solution set. And through discussions with other decision makers, you can see how your solutions might change depending on how you prioritize the criteria to come up with your solution set. Now, one way to help evaluate your decision is with the synthesized efficiency plot. So synthesized efficiency is defined as the desirability function score for a given solution at a particular weight, and we divide it by the best or the maximum desirability function score at that same weight. So what we're doing is comparing potential solutions to the best or most optimal solution, I would say optimal solution at any weight combination. So notice that this plot is very similar to the mixture plot. So again, on the x-axis we have the weight on the reliability, and on the y-axis is again our ID or index column. This plot is on a blue to white scale to help distinguish it from the mixture plot. So here a dark blue square is going to indicate that that particular solution at that weight combination has very similar behavior or performance in terms of the desirability function score compared to the best one. Whereas a value of 0 is going to say that there are larger trade-offs, right? It has much worse performance in terms of how you weight the criteria and the overall desirability function score. So things you want to look for in this plot are, do you have solutions that have dark to medium blue across all of the weight combinations? So for example, subpopulation 2 we saw before, when reliability was emphasized even with a weight of 0.1 all the way up to 1, right, it tended to be very high on our optimal list. It was either the second, third, or most critical solution identified. But when urgency was prioritized, it dropped from the top 4. However, note that we still have a lot of medium blue, dark blue, right, when urgency is emphasized. So even though it wasn't a top 4 solution, it performs very similarly to the best solution. The other thing you can look for is, do you see any solutions that have large trade-offs? So in this one, for example, solution 25, right, it has a very light square here indicating it doesn't perform very similarly to the top solution at this weight compared to very dark blue when reliability is emphasized. Right, so this is showing us there are large trade-offs for this solution in terms of the 2 criteria. So for example, let's look at weight of 0.15 again. Here is index 70, which if you recall from the mixture plot had the highest desirability function score at this weight combination. So by definition, its synthesized efficiency is 1. Compare this to index 20, which was not a top 4 solution at this weight combination, but has some dark medium blue and actually has a synthesized efficiency fairly high. So even though it wasn't the top 4 solution at this weight combination, right, it still is competitive at this weight combination. And you'll note that when reliability was more urgently prioritized, it has very dark blue. It was one of the most critical solutions. So even when urgency is more prioritized, right, this subpopulation is still a competitive choice. And again, here is index 2. So say we ignore reliability completely and just look at urgency, its synthesized efficiency is very similar to the optimal solution at this weight, indicating it is still a critical solution even at this weight combination. One final question that might arise is, well, how do you choose the value of n? Right? In the scenario we gave, it was more dictated by the resources available. They had resources for 4 subpopulations. They needed to choose 4 of them. In other scenarios, you might have more leeway in this choice of n. So this other plot, the n comparison plot, is a tool to help you evaluate the choice of n. So what this plot does is it considers the ratio of desirability function scores for the n+1th best solution to the nth best solution. Right, so for each weight combination, we're going to identify the top n solutions. So what we're doing is looking at the ratio of, well, what if we had chosen n+1 as the value of n? How would that n+1 solution compare to our nth best solution? Right, so in this plot, a high value suggests we may want to consider a larger value of n in our search, since the score of the next lowest solution has very similar performance to our current last choice. So this n comparison plot is shown here. So ideally, if we have a good choice of n, right, we would see lower values, right, across our weight combinations. In this example, right, we had some 5th best solutions that perform very similarly to the 4th best solution. So we may want to run our algorithm and say, what would happen if we wanted the top 5 subpopulations? How different would our solution set change? Okay, so what we've talked about here is, 1, using multiple criteria or objectives allows you to have more flexibility in your decision-making process. Right, this allows us to have a more informed decision by focusing on more criteria rather than just one. Right, we showed that using layered Pareto fronts can help focus on the best subset of candidates while still reducing the total number of options or solutions that need to be considered. Right, these graphical tools that we've presented can really help to understand the choices and help guide you to make a decision based on your own priorities. Now, I showed the example with just 2 criteria, reliability and urgency, but it is functional for more than that. And there is a jump add-in that is being distributed and can be downloaded as a jump add-in that can just be built into your regular jump program, and then you can use it. And we will have another video to show you how you can use that add-in to get the results that I showed you in this video. So that concludes our introduction to a top N front search using layer Pareto fronts. Thank you.